My name is Christoph Yao Gadese. I hold MPhils in Mathematics Education. I'm the one taking you through Math 101, Algebra and Trigonometry. We continue with Unit 4, which is on polynomial functions and linear programming. We'll deal with Section 3 on rational functions. Let's look at the section objectives. By the end of this section, you should be able to A. Distinguish between rational function and rational expression. B. Simplify two rational functions. C. Draw the graph of a rational function within a given domain. Use the remainder theorem to evaluate the remainder of a polynomial given a linear divisor. Use the factor theorem to determine the other factors of a polynomial expression given one of the factors. And lastly, draw the graph of a polynomial function with a given domain. Rational expressions and rational function. A rational function is defined as the quotient of two polynomial functions. So if you have f of x is equal to p of x over q of x, where p of x and q of x are two polynomial functions, then you have a rational function. Examples of rational functions. F of x is equal to x squared plus 1 all over x minus 1, where x is not equal to 1. F of x is equal to 2 of x is equal to 2x plus 1 all over x plus 3, where x is not equal to negative 3. So these are rational functions. Now, if we take off the f of x and the equal to sign, then we have rational expressions. Examples: 2t squared minus t minus 6 all over 4t squared plus 6t. Another example: y squared minus 4 all over 4y squared. Another one is x squared plus 1 all over x minus 1. Then 2x plus 1 all over x plus 3. So these are all examples of rational expressions because we have taken the f of x is equal to out. But the moment we introduce, say, g of x is equal to, before we write the expression, then it becomes a rational function. We can add rational functions. We can also find their differences. We can multiply them and we can divide them. Let's look at some example. Given that f of x is equal to x over x squared minus 1 and g of x is equal to 2 over x minus 1, find f of x minus g of x and state its domain. Let's look at the solution. F of x minus g of x is equal to, so we'll bring the function for f of x, which is x over x squared minus 1, minus we bring the function for g of x, which is 2 over x minus 1. Then when we look carefully at the denominator of f of x, we see that it's a difference of two squares. So we rewrite it as x over x plus 1 in one bracket, x minus 1 in another bracket, then minus 2 over x minus 1. We find the LCM. The LCM is x into bracket x plus 1, then into another bracket x minus 1. X plus 1 in one bracket, x minus 1 in another bracket will go into the LCM 1. 1 times x will give us x. Then x minus 1 will take away x minus 1, leaving x plus 1. X plus 1 will multiply 2. So we have 2 into bracket x plus 1. We simplify by using 2 to open the bracket. So we have x minus 2x minus 2 over into bracket x plus 1 into the other bracket x minus. Then when we simplify the denominator, we get x plus 2 over x plus 1 in one bracket, x minus 1 in the other bracket, and the answer is negative. So we show the negative sign there, because if you simplify the numerator, you get a negative answer at the numerator, which you bring to the middle of the fraction. The domain, therefore, is x such that x belongs to all real numbers, but x cannot be equal to plus or minus 1. Because if x is equal to plus 1, the function will be undefined. If it is equal to minus 1, the function will be undefined. Let's look at another example that involves division of rational expressions. So you have the first rational expression, x over x plus 1 and is being divided by another expression, which is in parentheses, 1 over x squared minus 1 minus 1 over x minus 1. To find the solution, we'll first put our attention on the second, the one at the right-hand side. And that expression, we first of all have to simplify. And we see that x squared minus 1 is difference of two squares. So we maintain the first expression x over x plus 1. We bring the division sign, then we open the bracket. Then the first expression in the bracket becomes 1 over into bracket x plus 1, multiplying another bracket which is x minus 1, then minus 1 over x minus 1. We find the LCM for the one at the right. The LCM is x plus 1 in one bracket, x minus 1 in another bracket, x plus 1 in one bracket, x minus 1 in the other bracket will go into the denominator 1. Then we use 1 to multiply 1, we have 1. And then we bring minus. Then x minus 1 will cancel x minus 1 and it will leave x plus 1. We use x plus 1 to multiply 1. We get x plus 1 in bracket. We still maintain the first rational expression divided by. Then when we simplify the one at the right, we will get negative x over x plus 1 in one bracket, x minus 1 in the other bracket. Then we maintain the first rational expression, and this time round, we change the division to multiplication, and then we do a reciprocal of the rational function at the right, so that the denominator goes up, x plus 1 in one bracket, x minus 1 in the other bracket, all over. Then the numerator comes down to negative x. Then we do cancellations and simplify, and we are left with 1 minus x as the answer. Let's look at graphs of rational function. To graph a rational function of the form f of x is equal to g of x over h of x, we are going to do two things. We will first identify the domain and also look for the restrictions. The domain will be made up of the values of x, but the restrictions are going to be given to us by where the graph will not exist. So they are normally given by the independent variables. And these independent variables are the ones that you cannot find in the domain. To look for these restrictions, you have to set the denominator to be equal to 0. Then you simplify for the values of x. Now, the rational function exhibit certain behaviors at its restrictions. Let's look at some of these behaviors. The first one is that the graph of the rational function will have a vertical asymptote at the restricted value. The second behavior is that the graph will exhibit a hole at the restricted value. Because the graph cannot exist at that point, there's a break which will be shown as a hole in the graph. Aside the rational functions, there are other polynomial functions. Let's look at them. A polynomial function may differ in terms of the degree, and the degree is the highest exponent of the function. So a general polynomial function of degree n is defined as p of x is equal to a subscript 0 plus a1x plus a2x squared plus a3 x cubed, and it continues till you get to the last one, which is a n xn. Before you get to the last one, you get to a term which is a n minus 1 x n minus 1. The a's are constant, where x is the variable. We can perform addition, subtraction, multiplication, and division on polynomial functions. Let's look at example 13. Find the sum of the following polynomial functions: 3x minus 7 and 3x squared minus 8x plus 5. Let's look at the solution. We will add the two polynomial functions, 3x minus 7 plus 3x squared minus 8x plus 5. To do this addition, we group like terms and add them. We see that 3x squared is the only one there. We don't have any term in exponent 2. So we write 3x squared. Then we have 3x and we have minus 8x. When we put the two together, we have minus 5x. Then we have negative 7 and 5. When we put the two together, we have negative 2. So the answer becomes 3x squared minus 5x minus 2. Let's look at another example, this time involving subtraction. You have g of x to be equal to 3x squared minus 4x plus 2, and f of x is equal to 2x cubed minus x squared plus 2x minus 3. Let's look at the solution. F of x minus g of x is equal to, so we bring f of x first, then minus g of x, because f of x comes first. Subtraction is not commutative. So we bring the function for f of x, which is 2x cubed minus x squared plus 2x minus 3. Then minus, because of the minus sign, we have to put the other function, g of x, in brackets. Then we use the minus sign to open the bracket. So that we'll have 2x cubed minus x squared plus 2x minus 3. Then minus 3x squared plus, because minus minus will give us plus. So minus minus 4x will give us plus 4x. And then minus plus will give us minus 2. We simplify. The one with exponent 3 is only 1, so 2x cubed. Then the one with exponent 2 are 2 minus x squared minus 3x squared. We put it together, we have minus 4x squared. Then 2x plus 4x will give us 6x. And then minus 3 minus 2 will give us minus 5 as the solution. Let's look at one that also involves multiplication. Find the product of x plus 2 and x cubed plus 2x minus 4. Solution: x plus 2 in one bracket, x cubed plus 2x minus 4 in another bracket. So we consider the first bracket, and then we use x to multiply the first bracket, and then we use plus 2 to multiply the second bracket. So x will multiply x cubed plus 2x minus 4. Then plus 2 will multiply the same thing, x cubed plus 2x minus 4. Then we expand. X times x cubed will give us x exponent 4. Then x times 2x will give us 2x squared. Then x minus 4 will give us minus 4x. Then plus, we now use 2 to open the bracket. We have 2x cubed plus 4x minus 8. Then we group like terms and simplify. X exponent 4 is the only one, so we maintain it. 2x exponent 3 is also the only one, we maintain it. Then 2x squared is also the only one, we maintain it. Then minus 8. Division of polynomial functions. If you have a polynomial function being divided by another polynomial function, the one at the top is called the dividend. Then the one that is doing the division is the divisor. And if you carry out this division, the answer can be expressed as the quotient. That is the number of times the divisor goes into the dividend. Then you have plus the remainder divided by the divisor. If we use the divisor to multiply through, we get the dividend is equal to divisor times quotient plus the remainder. If we let the dividend be f of x, then we let the quotient be q of x, and then the divisor be x minus a, and the remainder be r. We can write the whole thing to look like f of x, which is the dividend, is equal to the divisor, which is x minus a, times the quotient, which is q of x, then plus the remainder. If we set x minus a to be equal to 0, then it means that x will be equal to a. And if that happens, the divisor goes to 0. And so once the divisor goes to 0, the quotient also goes to 0. And so f of a will be equal to the remainder. And this is what we call the remainder theorem. That if you are given a factor and you make x the subject and you substitute it into the function, whatever answer you get becomes the remainder. Let's look at what the remainder theorem says. It states that the remainder, when a polynomial function is divided by x minus 1, is obtained by substituting a for x in the given function. Let's look at an example. Find the remainder when f of x is equal to 3x cubed plus 4x squared plus 3x plus 2 is divided by x plus 2. Solution. We first of all will let x plus 2 to be equal to 0. Then we make x the subject and we get negative 2. We substitute negative 2 into the function. So we have f of negative 2 is equal to 3 into bracket negative 2 cube plus 4 into bracket negative 2 squared plus 3 into bracket negative 2 plus 2. This gives us negative 24 plus 16 minus 6 plus 2, and it gives us negative 12. So what this means is that if you divide f of x, which is 3x cubed plus 4x squared plus 3x plus 2 by x plus 2, you get a remainder, and the remainder is negative 12. Let's look at another theorem, which we call factor theorem. And the factor theorem works the same way as the remainder theorem. The only difference is that for the factor theorem, the remainder is 0. So anytime the remainder is 0, then the x minus a is said to be a factor of the polynomial function. And so the theorem states that if x minus a is a factor of the polynomial function, f of x, then f of a is equal to r, which is equal to 0. That means x minus a is a factor of the polynomial f of if and only if f of a is equal to 0. Let's look at some examples. Find the values of a, b, and c. If x plus 2, x minus 3, and 2x plus 1 are factors of ax cubed plus bx squared plus cx minus 6. Let's look at the solution. We take the first one, the first factor, x plus 2. We make x the subject, we get negative 2. So we do f of negative 2. What it means is that we are going to substitute f is equal to negative 2 into the given polynomial function. So when we simplify, we get negative 8a plus 4b minus 2c is equal to c. We call that one equation 1. We take the second factor, x minus 3. We make x the subject and x is equal to 3. We substitute it into the given polynomial and simplify. We have 27a plus 9b plus 3c is equal to 6. That gives us equation 2. We take the last factor, which is 2x plus 1. We make x the subject, and we get negative 1 over 2. We substitute negative 1 over 2 into the polynomial, and we get negative a plus 2b minus 4c is equal to 48. Equation 3. We consider those three equations that we have formed, and we solve them simultaneously. Then you will get a to be 2, b to be negative 1, and c to be negative 13. We will substitute these ones into the given expression, and that becomes 2x cubed minus x squared minus 13x minus 6. Let's now look at how to graph some of these polynomial functions. And let's consider the example. Draw the graph of y is equal to 2x cubed minus 9x squared plus x plus 12 in the interval negative 3 less than or equal to x less than or equal to 6. To solve this, we'll have to draw a table of values, just as we did when we're doing the quadratic functions, and then plot the pair of values that we will have, and then join the points with lines to have the curve. Here is the table. The first row is made up of the range of values of x from negative 3 to 6. Then the terms of the polynomial 2x cubed comes as the second row, negative 9x squared come next, followed by x. Then we repeat the constant term 12. So we put the values of x into each of them and simplify. For example, we put negative 3 into 2x cubed, we get negative 54. We put negative 2 into it, we get negative 16. We put negative 1 into it, we get negative 2. We substitute 0 into it, we get 0. We put 1 into it, we get 2. We put 2 into it, we get 16. We put 3 into it, we get 54. We put 4 into it, we get 128. We put 5, we get 250. And we put 6, we get 430. We do it for each of the terms, and then we add the answers to get the corresponding y values. Then we plot the x values against the y value. This is how the graph will look like. The degree of the polynomial is 3, and so the graph will have 2 turning points. It turns twice. You can get more examples on this and try your hands on them and discuss your answers with your colleagues. Thank you for your attention.